Okay, welcome back to section 1.5, techniques for evaluating limits. This is Mrs. Allen, and we are talking about limits. And in the previous video, we talked about evaluating limits graphically and numerically. And that's always a very handy tool, especially if you have a graphing calculator to kind of see, hey, what's a picture of this graph look like if I were to put the function in? It's very, very helpful. But we're going to now talk about evaluating limits algebraically. So one of the techniques has to do with dividing out. In fact, I have it up there. Finding the limit of a function, number one, the dividing out technique. And you see I have Cookie Monster there. If you ask Siri, what is 0 divided by 0? Cookie Monster has a little story to go along with that. But nonetheless, 0 divided by 0 is what we call an indeterminate form. We cannot determine what the form is actually equal to or equivalent to. So what we have to do is do a little work algebraically on it. So when we take the limit of x cubed minus 1 over x minus 1, you can see that we get the 0 over 0, an indeterminate form. So we're going to look to manipulate the expression. Now, noting that the top can be factored as the difference of two cubes. And I put my little method when I taught this in algebra. It's same, opposite, plus, so the SOP method for the difference of two cubes. So what we're going to do is we're going to now take the limit as x approaches 1, and I'm going to factor the numerator, so that's going to be x minus 1, and then it's times the quantity x squared plus, so remember the same, opposite, plus x, and then it's plus 1, SOP, same, opposite, plus. And then that would then be over x minus 1. And we're going to simplify this expression. We're going to cancel the x minus 1s then. And so now I'm taking the limit as x approaches 1 of x squared plus x plus 1. And that's a polynomial expression. So I can really do a direct substitution and plug in 1. Because it's a polynomial, it's going to be equal, the limit is going to be equal to f of 1. So we just do 1 plus 1, 1 squared plus 1 plus 1, and that's going to be 3. So then, therefore, the limit as x approaches 1 of x cubed minus 1 all over x minus 1 is equal to 3. And you've kind of guessed that the graph itself is going to look like a quadratic, except it's going to have a hole in it at 1, 3. Okay, so there you go. Here we're on to example 6 now. If you need to stop the video, review it, rewind, and check it out again, do that. Here's the next one, finding the limit of a function. The dividing out technique is going to be used here. So we first determine that it's an indeterminate form before we start to factor this. Because you might be able to plug in right away, and maybe you get 10 for an answer in some of these problems. And that's not indeterminate. But when you get 0 over 0, look for a way to manipulate the expression. So if we have the limit of that expression, a quadratic over x plus 3, I'm going to say, all right, well, let's see if since it's 0 over 0, it's an indeterminate form, something should cancel. So what I'm going to do is factor the numerator as x plus 3 and then x minus 2. I often look, when it's 0 over 0, I look at what the denominator is, and and I just say, that x plus 3 is going to have to cancel. So you can kind of force the issue with your factoring. Okay, cancel the x plus 3's, and now we're taking the limit as x then approaches negative 3 of x minus 2. And that's just going to be negative 3 minus 2, which is negative 5. And you can see on the graph that I had drawn here, there's a hole on the graph of x minus 2. This is just the graph of y equals x minus 2 with the stipulation that there is a hole in the graph at negative 3, negative 5. Okay, so the limit is negative 5, and you can see as you're approaching from the right and the left. Okay, it's example 6, example 7. This one's a little different. This brings about the second method for finding the limit, and this is called the rationalizing technique. So you recall that when you were in Algebra 2 and pre-calculus, you may have had to rationalize the denominator as if you couldn't have a square root in the denominator. or a cube root or something, a root at all. So in this section, I want you to focus back. Remember the a squared minus b squared form, a minus b, a plus b. So if you look at the numerator of this limit, okay, notice that when we put 0, and we have 0 over 0, so if we kind of turn, looks like an unhappy face, but not unhappy for too long. So we have the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x, indeterminate, but we can use this fact that if we can form an a squared minus b squared form, notice what we get here. We get x plus 1 minus 1. So the a being the square root of x plus 1, the b being 1, if I were to multiply this expression by 1, looking like that, then I can get rid of the radical problem. And notice what you get as a result. You get x plus 1 minus 1, which is just x. So let's play with this. So now we have the limit as x approaches 0 of x plus 1 minus 1 in the numerator. And in the denominator, we have x times the square root, the quantity, the square root of x plus 1 plus 1. Now, the thing I used to forget to do is sometimes I'd forget to multiply the denominator when I was rationalizing. So you can't forget to do that. So I'll stick with black. So now we have the limit as x approaches 0 of x all over x times the square root of x plus 1 plus 1. Now, if you notice now, it's still indeterminate, but you have an x in the numerator as a factor and the denominator, so we can now cancel those. And so now we're taking the limit as x. We have the limit as x approaches 0 of 1 over that square root of x plus 1 plus 1, which is then, we're ready now to simplify. This is going to be 1 in the numerator and do a direct substitution with your x. So you get the square root of 0 plus 1 plus 1. So this is going to be 1 over 1 plus 1. So your answer, your limit, is going to equal, I don't know where to put this now, the limit as x approaches 0 of the square root of x plus 1 minus 1 over x will equal 1 over 2. And I'll box that up just to clarify. Okay. Alrighty, so let's see if we can get one more in here. And let's talk about this finding one-sided limits again. So finding the limit as x approaches 0 from the left and the limit as x approaches 0 from the right for the function f of x is equal to the absolute value of 2x over x. So before I get started in this, I want to simplify the expression. This sometimes needs a little bit of work. If you are on the right side of x is equal to 0, this expression, the absolute value of 2x over x, is 2x over x, which is equal to 2. Okay? So now, I'm going to, remember, this is f of x. So this is y is equal to 2, if you will. Okay? So simplifying absolute values, if x is positive or to the right of 0, then it's just 2x over x. However, if it's to the left of 0, then whatever x is still x, right? The absolute value then is going to turn this into the opposite of 2x. So your function value then will be negative 2 for all x, and this will be y is equal to negative 2. So if we're going to take the limit as x approaches 0, at this time, we're just going to say the limit as x approaches 0 of the absolute value of 2x over x does not exist. It does not exist. And let's put a little note in there doesn't exist because the left and the right limits are not the same. So that's the way we say that, okay? The left and right aren't, let's just write it like this, equal, okay? So this side is equal to 2. This side is equal to, oh, I'm sorry, I got them backwards. Do I have them backwards? I most certainly do. How did that happen? Let's just change that real quick so it's right. Okay, so this is on the right-hand side, and this is on the left-hand side. So that's 2, and that's -2. And so those are not equal, so the limit does not exist. Okay? So that's it for this video. I'm going to pick up with the last video of this section to complete 2 more problems, and that should be it. And so this is Mrs. Allen signing out. Have a nice day. I'll see you when I see you.